Good afternoon, everybody. This is Nancy Badu speaking. I'm an Associate Director with the Steel Construction Institute, and I'd like to welcome you to this afternoon's webinar. By popular demand, we have put on this webinar covering the topic of protective coatings for steel structures. There's a lot of interest in this subject, and I'm really pleased to welcome Malcolm Morris to be our guest speaker. Now, he works for the SCI member company Sherwin-Wiilliams and has a wealth of experience on this topic. So that's enough from me. I'm now going to hand over to Malcolm.
Thank you, Nancy, and thank you to everybody who's taken some time out of your busy day to listen to some old guy talking about paint drying. It's an extensive subject, and it's quite often been a source of irritation to me that people just think of it, oh, it's only a coat of paint, and hopefully the next hour or so will demonstrate that this only a coat of paint will actually form the difference between protecting your precious steel asset and disaster happening either through corrosion or fire damage. So moving on, a little bit about me. This is me. I'm 46, nearly 47 years in the industry now. I fell into the protective paint industry with Lee's Paints in 1978, quite by accident. It was only a temporary job, and I'm still here temporarily all this time later. But it's been an interesting career. I'm a chemist by background. Main part of my early career was in R&D. Then I went to technical service as an inspector, and now my main job is with training and standards and managing the technical support function within Sherwin-Wiilliams. So any queries from external or internal colleagues come through my team, and we hope to answer them. If we can't answer them, then find somebody who does. I will be retiring from the corporate world sometime this year, but I will be carrying on a little bit under my own steam, carry on with training, plus some advisory work and also standards development work, which forms a large part of my life. I'm involved with a lot of the technical standards which relate to protective coatings. So that's me. Very brief overview of today's talk. I'm talking about steel substrates and the features and benefits, the corrosion process and how we protect against corrosion, mitigate the effects of corrosion, and also about the reaction of steel to fire. Obviously, fire loses its structural load-bearing capacity in a fire situation, so this again can be mitigated by the use of reactive intumescent coatings. Also, a word about quality control, because this is the key to success or failure in a protective paint system. The best paint in the world will fail if it's not controlled at each stage of the specification, application, and post-application stages of the process. And also look at some common issues and defects, and hopefully by the end of it we will have some better idea about the whole process. So steel, I'm preaching to the converted here, because obviously you're all involved with steel, and you know, either manufacture or utilize steel in your daily job. But steel, you don't need me to tell you, it is very widely used in construction. The City of London there has many steel structures which are only possible with the use of steel. Steel is lightweight, it's flexible, it's economical, and it's got this great design potential that it can go higher than other construction materials, and also these wonderful designs that the architects conceive and draw to fruition. As good as steel is, it does have two fundamental drawbacks. One is the natural drive for it to corrode back to its native stable oxide state. Steel being principally iron has sat in the ground since the formation of planet Earth billions of years as iron oxide. That's a stable state, that's where it wants to be. Humankind digs it out to the ground and converts it to steel with a huge amount of energy, but steel doesn't want to be steel, it wants to get back to its native natural oxide state. And also the drawback to steel is it loses its load bearing capacity in a fire situation. But both these drawbacks can be mitigated by the use of properly specified and applied protective surface coatings. We start off with corrosion. Corrosion, various definitions, but the one I like is the deterioration of a substance, usually a metal. Here we're talking about steel in particular, due to reaction or interaction with its environment. And in the everyday context, we're talking about steel turning into rust. And it's a big deal. If we didn't protect steel assets from corrosion, the cost of replacement would be approximately 3 to 4% of the GDP of any industrialized nation. Not to mention the health and safety issues of corrosion and fire damage. So an old estimate, this is a 2010 estimate, global cost for corrosion $2.5 trillion. And in the UK, the most recent survey I could find was 2016. That was £46 billion per annum. And that's obviously 9 years. Costs have gone up quite a lot. It's probably much closer to 100 billion, I know, but who knows what the actual cost is, but it's a lot. And why does corrosion occur? Well, most metals exist in their natural form as metal oxides or metal ores. And this is, as I said before, the most stable chemical form. This is where they sat in the earth for millions, billions of years. But metal ores are dug up and then they are extracted and smelted with reducing agents to yield a pure metal. So in the case of iron, we're talking reduction of iron oxide into metallic iron, which is then blended with other alloying elements to form the steel. But most of these pure metals are unstable. They readily react with oxygen and water to revert to their stable natural oxide state. So we can never prevent corrosion. Anybody who says corrosion prevention is either lying or in a dream world, but we can protect against corrosion to delay and mitigate that inevitable process. And steel in particular is an alloy. Say many different types of steel. I don't need to tell you guys, you're more expert in the composition of steel than I am, but steel is alloyed with chromium, molybdenum, other elements, along with carbon to form different grades of steel, which will give different physical properties. But the differences in the structure, I'll just quickly pass forward. That's a micrograph of steel. You can see it's not homogeneous, it's not even, it's lots and lots of different areas of different compositions and crystals, which form a very mixed up composite composition. And some areas will be more reactive with respect to their neighbours. So some areas will go anodic or reactive, and their next door neighbour will be less reactive or cathodic. These are all spread all over the surface of the metal substrate. Steel itself is a conductive metal, and then you can actually get an electrical circuit between the anodic and cathodic areas, between the metallic pathway and then the outside environment, sometimes called the electrolyte. But the electrolyte or environment could be moist air, it could be aqueous immersion, it could be chemical immersion, but this external environment will affect and complete the corrosion circuit. And the more electrically conductive that external environment is, then the more efficient the corrosion mechanism will be. That's why marine environment is much more corrosive than an internal urban environment, far from the coast, because there's more salty air is more conductive than purer air. So that environment will form a huge part of the corrosion circuit. So corrosion is what we call an electrochemical reaction, because, as I say, we're effectively creating an electrical circuit. So the acronym there is ACME, easily remembered from the fondly remembered Bugs Bunny and Roadrunner cartoons. The Acme Corporation supplied the Roadrunners implements of mass destruction, which never worked, but that's the easy acronym. So A, the anode, this is the reactive area on a steel substrate, which dissolves to form ferrous ions and free electrons. The cathode is the less reactive next door neighbour, if you like. whereby the electrons and the ferrous ions will migrate to precipitate iron oxide products in conjunction with oxygen and water. This is effectively rust. The metallic pathway is the steel item itself, whatever the job is, and then the electrolyte is the surrounding environment. In terms of controlling corrosion, we can't control the anode or the cathode because they're there. The metallic pathway is the job itself, but can't control that because it just is intrinsically part of the circuit. But we can control the electrolyte. If we can exclude the electrolyte from the substrate, then effectively we can break that electrical circuit and mitigate the actual chemical reaction of the corrosion cell. This diagram explains it in a little bit more detail. You can see on the left-hand side an anodic site, which is more reactive than its next door neighbour to the right, the cathodic site. The steel or iron dissolves at the anode and then releases ferrous ions into the conductive electrolyte on the outside, and then the electrons transfer to the cathodic site next door. At the cathode, the ferrous ions and the electrons combine with oxygen and water. They will perform this chemical reaction to precipitate a hydrated ferric oxide, which is red rust. Oxygen is the important fifth element to the cell, if you like. Without oxygen, corrosion will not happen. The best analogy for this is if you think of the shipwreck, the wreck of the Titanic. There's divers with cameras been down there. The wreck is still there after 100 odd years at the bottom of the Atlantic. Well, why is it not corroded? Because it's a chunk of steel that's been bathed in seawater for 100 plus years. But basically, there's no oxygen at the bottom of the sea. Below 20 meters, there's no dissolved oxygen in the sea. Without that oxygen, that corrosion reaction cannot take place, and the wreck is still largely intact. Bit of chemistry for those who are interested. Maybe not go away, make a quick cup of tea. But the anodic reaction there, the iron goes into solution as ferrous ions, liberating electrons. The cathodic reaction next door, those electrons combine with oxygen and water to form hydroxyl ions, and the whole thing combines to form the species at the bottom right hand corner there, hydrated ferric oxide, which is red rust. There are also other corrosion mechanisms that can take place in buried situations, buried underground, or in low oxygen situations such as crevices, but we don't really have time to go into those at the moment. But that is a general, if you like, open air corrosion mechanism. So how do we control corrosion? As I say, we can't prevent it. It's a natural process driven by the laws of thermodynamics, and so it's like trying to stop the tide coming in. First of all, we can design our structures to be less prone to corrosion. If structures have things like water traps and back-to-back steel eliminated from the design, that will greatly assist the longevity of the particular design. We can put chemical inhibitors into paints. The most common one you'll see out there is what we call zinc phosphate, which is a chemical which chemically inhibits the corrosion chemical reaction. That's the most common one these days. I mean, when I first started, it used to be great fun because we had things like red lead and zinc chromate, which were superb corrosion inhibitors, but unfortunately, they are very toxic, and obviously eliminating toxic raw materials is a great part of the work of the paint formulators these days, and we can only use relatively safe raw materials these days, so zinc phosphate is the main one. Sacrificial paints, metallic zinc can be incorporated into primers to form what we call zinc-rich primers, and the zinc there acts as a false anode and will actually corrode preferentially to the steel in a corrosion situation. So they are very effective corrosion protection primers. And also barrier coatings. As I say, if you can eliminate that electrolyte or outside environment from the steel to stop water and oxygen getting to the steel, then you will greatly reduce the rate at which corrosion occurs. And we use pigments like glass flake, MIOs, micaceous iron oxide. So these pigments will give a very good overlapping barrier effect within the coating. Corrosion protection is governed by an international standard, ISO12944, which is the international standard for corrosion protection of steel structures by protective paint systems. And this is effectively the Bible by which paint manufacturers will develop paints and develop specifications for corrosion protection. It comes in 9 thrilling installments, which after the introduction, these are the different parts. And the key ones there are part 2, classification of the environment, design considerations we mentioned. It suggests best practices to avoid corrosion traps. As surface preparation, because that's a key point to having a successful coating system. Protective paint systems are suggested for different environments and durabilities. And then all sorts of ancillary sections about proving test methods, execution, and specifications. Part 9 was added on. That used to be a separate standard called ISO12944. That's specifically for offshore structures, which are obviously very corrosive environment. But the key things out of 12944, first of all, is the classification of the environment. And this is a concept called corrosivity, which I wasn't sure was a real word, but it's in the standard, so it must be a real word. And C1 corrosivity is very low. That will be an internal, dry, controlled environment. And then it ramps up through C2, which will be internal and controlled. It could be external. It's very low pollution and low dry environment, but I don't believe there's anywhere, certainly in the UK or Northern Europe, that's really C2 external. C3 will be a typical urban environment. It could be an internal wet environment, such as a kitchen where you get a lot of condensation. Going to scale again, C4 will be high, so that will be an external environment getting close to the coast where you've got some salinity blowing in from the sea air. It could be an internal, very wet environment like a chemical plant or a swimming pool. Then you've got C5, which is very high corrosivity, so that would be a marine environment on the coast or very highly polluted in a chemical works or whatever. And then CX is X stands for extreme, which is very high offshore, so that will be an offshore oil or gas rig, for example, where you've got very, very high salinity and being lashed by the sea. Corrosivity scientifically is defined by the rate of metal loss on a particular location, but that's quite a slow scientific process, and people can't afford to put steel coupons into an environment and wait for X years to see how much degradation there is. So the standard does actually have verbal descriptions and examples, and it's up to the client to decide what corrosivity their particular structure will be, and then the paint manufacturer will specify according to their definition of the corrosive environment. Examples there: C1 environment, internal dry control. That's my desk. So there's not what goes on there. Put a piece of steel in that environment, and it will pretty much stay there, provided nobody steals it. No corrosion whatsoever. C2 example, that's a train maintenance shed at the North Pole Depot in London for Great Western Railways, and that is covered, so there's no direct weather. Obviously, those doors are constantly opening. There's no heating in there, so it could get condensation, so a higher corrosion potential. That's an example of a C3 urban environment. That's the Tinsley viaduct in Sheffield, which carries the M1 past the Meadowhall shopping centre. That probably used to be C4 when the cooling tower on the right there, when that used to be a power station, that was probably a C4 due to the pollution from the power station, but then that cooling tower is actually gone. So that is probably a C3 urban environment in Sheffield. That's C5, that's yours truly on top of the Forth Bridge, trying definitely on some terrified in an ill-fitting network rail boiler suit. But obviously the Forth Bridge is extremely exposed to the North Seas and the Firth of Forth, and that is a very corrosive environment indeed. So that would require a very high quality paint specification to make it last for, well, 20 plus years. It's actually parts of it when they started the job are over 20 years old now and they're still holding up very well. So that's a good example of a high performance paint system there. 12944 also covers categories for immersion, freshwater, seawater, buried in the ground, or immersion with cathodic protection. And then it defines protective paint systems for the different corrosive environments and based on durability. Now, durability is an interesting word, and it's defined in the standard. It's not a warranty period. You can't say that, oh yes, I've got a 20-year or 25-year durable paint system. It will not break down at all within that 25 years, because paint systems out there in the big world are subjected to a lot of external stresses. You've got the weather, you've got hot cold cycling, wet dry cycling, you could have abrasion, you could have mechanical damage, etc. So durability is defined as the period which a paint system will be expected to last, with an agreed schedule of inspection and minor maintenance. So you expect within that durability period for some degradation to happen. It could be through mechanical damage, it could be through a weak spot in the coating system, or any minor damage or minor breakdown will be expected to be identified through inspection, and then minor maintenance carried out throughout that durability period to maintain the time to first major maintenance, if you like. And those are the durability periods and standards. Most specs are either high or very high durability that we're going to be dealing with here. You very rarely get low durability specifications required. Part 6 of the standard has laboratory performance, so we will test, as paint manufacturers, test any systems defined by the standards to make sure that they comply with the set of accelerated test criteria. So there's things like salt spray, humidity, immersion, and cyclic testing, and there are various limits which the paint systems must comply with to confirm that they will comply with the corrosion and durability requirements. We, as paint manufacturers, pretty much all the paint manufacturers, will externally verify with third-party testing with independent labs to verify their paint systems. 12944 is used for the majority of mainstream structural steel specifications. Many of the larger authorities will have their own paint specifications. So, for example, in the UK, highways agencies and the Network Rail have their own independent paint specifications, quite detailed documents which will have their own pre-qualification criteria and things that you have to do to qualify your coatings to their requirements. And also oil and gas companies will also tend to have their own specifications. You may come across a spec called NORSOC, which is an oil and gas specification. I can't tell you what the acronym is because it's in Norwegian, but it's basically a consortium of paint manufacturers, asset owners, test houses within the Norwegian sector of the oil and gas industry. They've developed a very demanding specification, so you know that if you've got a NORSOC approved spec, it really is a very high performance spec indeed. IOGP is the Institute of Oil and Gas Producers, and they also have their own specifications, as do many of the oil companies, so Shell, Exxon, they have their own specs. Will be principally based around 12944 Part 9, but they have additional requirements as well. And these external corrosion specifications all have to be third-party verified, so you're not just taking the paint manufacturer's word that this is a good system. You know, it will be externally certified as well. So that is a very quick overview of corrosion protection. Looking forward now on intumescent coatings. The verb to intumesce means to swell up, and this is effectively what the fire protection coatings do. Intumescent coatings are used to protect steel and mitigate against the effect of temperature rise in a fire situation. So different types of intumescent coating for civil construction, and that's different to the oil, gas and chemical facilities, mainly because the potential source of fuel in civil construction, the main source of fuel will be what they call cellulosic materials, so wood-based, paper, furniture, that kind of thing. That's what they call a cellulosic fire, which is different to oil, gas and chemicals, where the principal source of fuel in a fire, God forbid, is what we call hydrocarbons. So it will be natural gas, LPG, crude oil, various other flammable chemicals, and oil and gas hydrocarbon fire is much more aggressive and dangerous, if you like, to a large extent than civil construction. So we have different products for the two different types of fire. But an interesting coating, it looks like ordinary paint. It applies mostly through standard spray kit. It goes on a bit thicker than traditional corrosion protection coatings, but in a fire situation, the pigments in the coating provide a series of chemical reactions which swell up and form a carbon char, which forms effectively an insulating blanket around the steel structure. And this insulates the steel from the effect of the fire and delays the rate at which the steel heats up in the fire situation. That is typical structural steel, which I don't need to introduce any of you guys to. I'm sure you're well familiar with that. But why do we need to protect steel? Well, in a fire situation, steel heats up, it loses strength, and very, very quickly, over above about 375 degrees centigrade. Typically, an average steel beam will lose about half its structural strength over above 500 degrees C. So anywhere between 400 and 600 degrees C, there's a rapid decrease in the load bearing capacity of structural steel, and above critical strength, obviously you're in danger of building collapsing. So that's what we're aiming to do with reactive fire protection steel coatings, is to mitigate the effects of that fire and preserve the structure for as long as possible. So we have a series of what we call standard fires. So there are British standards, European standards, American standards, many, many different standards which will effectively create a standard fire which we test against. So in a British standard fire situation, an average piece of steel unprotected hits that critical temperature around about 550 degrees C in about 15 to 20 minutes, or typically 17 minutes. It depends on the actual size of the steel, we'll see in a minute. But what we're aiming to do is increase that 15 to 20 minutes to 60 minutes or 90 minutes or even 2 hours. And that's why people talk about 60 minutes, 90 minutes, 2 hours fire protection. It is that extended period which we are aiming to preserve the integrity of that steel structure. In America, it's slightly different because they're still looking in old money, so they're testing to 1100 degrees Fahrenheit. That's the UL underwriters laboratory testing, but in effect, it's the same concept, no matter which test you are testing to. And the amount of fire protection you need is different to corrosion protection, because basically, putting very simplistically, for corrosion protection, the more corrosive the environment, the longer you want it to last, and the more paint you put on. It's not quite as simple as that, but it's independent of the actual size of the steel section you're coating. With fire protection, it's different because there are two units of measuring the effectively the sections factor of the steel, which is basically how thin and slender or how thick and chunky the steel is. And so you've got two steel sections there, a thin slender piece on the left, thicker chunky piece on the right. And if you put those two pieces of steel into a fire, the same fire, that thin slender piece is going to heat up a lot quicker because there's much less metal mass there than the thick chunky piece. The thicker the steel, the more heat sink you got from the mass of the steel, and so it will heat up correspondingly slower. So it goes rationally there to give the same amount of fire protection. You're going to need to put more thickness of fire protection on the thinner slender piece than the thicker chunkier piece. And so there are two measurements on the BS British standard. They measure what's called the HP over A, which is the heated perimeter, the outside length, if you like, of the steel divided by the cross-sectional area. Or comparatively, on the European standard, they measure the exposed surface against the overall volume of the steel, so that's the A over V. It's the same sort of concept, but slightly different numbers, and the European method, the A over V, gives a more conservative figure. You actually have to put more paint on to give protection on the European standards than the British standards, and the industry is moving over more towards the European, so the British standard will probably disappear very, very shortly. So different drivers, different standards behind the fire protection specifications. There are the so-called Eurocodes, which is the BSAN 199X series, which give you general guidance on structural fire design and how to specify the fire protection coatings. These are also encapsulated in the ASFP, is the Fire Protection Manufacturers Trade Association. They have what we call the Yellow Book, which is also the, if you like, the Bible of how to define fire protection. Currently on to revision 6 now. I think part 1 is revision 6 has just come out there. And also the building regulations, approved document B or ADB. And all these documents will be used by fire engineers to define for a particular structure how much fire protection you need. So it's all based on the occupancy of the building, whether it's for human habitation or not, the height of the building, whether or not the building's got sprinkler systems or secondary fire protection. All these factors will define how long, whether it's 60 minutes, 90 minutes, 120 minutes fire protection that is needed. And that will be the regulations which define that. It's all very, very tightly regulated, particularly since the Grenfell disaster. Unfortunately, most of these type of legislations are disaster driven. So the offshore oil and gas was very much tightened up following the Piper Alpha disaster in the 1980s. And since the Grenfell disaster, the actual design and legalities behind fire protection are very much more tightened since Grenfell, because there were a lot of errors and negligence around that time, and these have all been timed up with the so-called golden thread, which is a traceability of responsibility right from the design, application, quality control of any fire protection system. It's rightly tightened up the situation quite dramatically. So this is an example of the standard furnace curve, which is the blue line at the top, which could be defined by a British standard or European standard or American standard. And it's a similar sort of concept. The blue, the test furnace is heated up according to the blue time and temperature curve. If you put a piece of untreated, unprotected steel into that furnace, it would rise according to the red curve in the middle, which is basically following the furnace curve with a bit of a lag because of the heat sink of the steel. Then the green line at the bottom is the line which would be given by a protected piece of steel, and that will obviously stay much lower. And the aim is to keep the green line at the bottom below the critical temperature, whether it's 550 or 400 or whatever. That'll be defined by the Eurocodes. But the pieces of steel are basically put into furnaces, and the rate of increase of temperature of the steel itself is monitored by thermocouples and mapped out, and the regulatory bodies will give you the fire rating of your coating depending on the performance in the furnace. There are 3 stages of intumescent char formation. The red area at the start of the graph is basically the paint system heating up according to the furnace. There's not much reaction happening until the paint reaches about 275 degrees C, and then the black line in the middle is where the curve actually flattens off a little bit. This is where the chemical reactions are taking place to form the carbon char. These chemical reactions are actually what they call endothermic. They absorb heat out of the fire, so the actual curve flattens off a little bit there because of the endothermic heat absorption effect of the chemical reaction. Then after about half an hour, the char formation is complete. Your steel is encapsulated within the carbon blanket, and then it's just basically the insulating effect of the carbon blanket protecting the steel and insulating it for hopefully up to your 60-minute or 90-minute or 2-hour period. How do they work? Well, the key raw materials in classic intumescent formulations are an acid catalyst such as APP, ammonium polyphosphate, which decomposes in the fire situation to yield phosphoric acid. That phosphoric acid then reacts with what they call a carbonific, which is pentaerythritol. Typically, that's a complex alcohol. The acid reacts with that to dehydrate it and form a huge amount of carbon char, soot effectively. And then what we call spumific, which is typically something called melamine, which decomposes to give nitrogen gas in the fire situation, which expands the char up into a foam, and that forms the carbon char. The fourth element there is the organic binder, which the coating is based on. Effectively, as the fire heats up, that binder melts and holds the whole thing together. So you've got this exotic cocktail of melting binder, carbon being formed, and then spumific blowing it up into a foam, a little bit like shaving foam coming out of a can. The whole thing foams up into this wonderful carbon blanket, which will give it an insulating effect. And then this video here in the technology works, which thankfully it does. That's a time lapse. This video is courtesy of Nullify Limited, and that shows the paint film expanding up, and typically your paint film will expand. I'll just play that again because I like it, just so you can see the effect again. Typically between 20 and 100 times its original film thickness. Most commercial HMSs will expand to typically about 30 to 50 times the original thickness, but that carbon blanket blows up there and forms the carbon char. This is another video which shows the effect of that's a vertical column inside a test furnace. It's a very hostile environment. The wires leading off of the thermocouples, which are attached to the steel itself, and they will measure the steel temperature against the furnace temperature, and that's where we get these graphs produced. And from the test data, we can form the sets of loadings, which will determine how much HMS you need for a particular section type. So testing and certification, obviously fire protection is a very crucial part of any building design, and particularly post-Grenfell, there's a huge amount of certification required, and everything now has to be tested and certified and verified to the nth degree, because the Grenfell disaster particularly highlighted that there's a huge amount of everybody thought everybody else was doing the job, and it turns out that nobody was doing the job, and there was also elements of well, criminal negligence in some cases. So it is now absolutely nailed down, because we're talking about saving lives here. So it's very important. So typically, as paint manufacturers, we have in-house test furnaces. You can see on the left-hand ones, the column slot in there. These furnaces will be heated up, and we do our own internal test data. We can't just use internal test data, because everything has to be verified third party, so that nobody's cheating the system. So we then take our formulations that we screened and take them to external test houses, which are at various dotted around the UK. And these test houses will then retest our formulations and produce the actual raw data from which the paint manufacturer will produce their fire test loadings. That particular photograph shows what they call a loading beam test. The beam on the right hand side is actually on a hydraulic ram, so that will simulate not just the fire situation from the heat of the furnace, but actually that beam is under a defined load, so it will actually test the behaviour of the section under a loaded situation. This is what they call a blast test. Effectively, this test proves what would happen in the event of an explosion preceding a fire, because if there is an explosion, then what you don't want is for the blast to blow off the fire protection coating, and it all ends up on the floor. So this is done at an external test house, where the beams are set up at the end of that container, which is filled with a gas and air mixture, which will shortly be torched, and there's an enormous pop and bang. People have retreated to there it goes. So probably as well the sound isn't looking on this one, but you get the general idea that there's a fair old force being put on that coating, and those sections will then be taken out and tested, just to make sure that the fire performance test of the coating is the same after the blast as it was before the blast. So it's quite an important test that we perform there. Different market sectors, as I mentioned before, for cellulosic fire, that's buildings effectively. You can have what we call on-site application, which is where the steel is fabricated, primer coat applied, and then the steel is sent to site, the building is erected, and then the intermediate is put on site while the structure is being erected. This will typically use water-based or solvent-based single pack coatings. It's a cheaper process than what they call in-shop application, but it's more challenging because obviously the steel's up in the air, and if you're trying to paint steel that's many stories up in the air with the associated weather conditions, and yeah, the paint is half it's disappearing over the spray down to the next door building. It's a more challenging process, also more difficult to do quality control because you need access to these different situations. In-shop application is performed by the largest steel fabricators in shop. This is where they have large production lines where the steel sections are blasted, fabricated, and then painted with the primer and also the intumescent coating to give you coated sections, which are then sent to site, ready coated, they're then erected, and there's only minor touch-up required for damage repair and also for any jointed connections which need touching up. Technically it's better because the steel is on trestles. It's much easier for the applicator to reach and do a proper spray job, a good spray job on the sections. It's also better to inspect because again the steel is at easy height, good access, and the disadvantage is more expensive and it takes longer because obviously there's a period where the steel is drying in the shop, and that kind of backlogs up, and the speed of drying it is crucial there. But it is technically a much better process. But courses for courses, some people prefer one, others prefer the other. And then the different comparisons there between civil and oil and gas and chemicals. Basically, civil construction will use typically acrylic materials, or whereas oil and gas will have to use epoxy, very durable materials for the durability required in oil and gas situations offshore, and also for the intense aggressive nature of the hydrocarbon fire. But the durability of intumescent coatings is also a big question mark because intumescent coatings are designed to give fire protection, and inherently the raw materials used in there are quite water sensitive, so intumescent coatings can be susceptible to weather damage if they're not adequately protected. So you have to be careful which intumescent you specify in which environment, and also careful selection of protective sealer coats to protect the intumescent from damage from water ingress. Quality control wise, quality control is crucial to any protective coating system. We can make the best coating in the world, and every paint manufacturer out there will tell me they do. Joking apart, you know, the quality of coating is very good, but if you don't get all parts of the application and specification procedures correct, then you know the best paint system in the world is going to fail. So the ideal hold points with quality control should form a distinct view and approve systems. First of all, a suitable paint specification from either ISO12944 or the paint manufacturers, and agreed loadings for fire protection system. This has to be agreed between all parties, and everybody knows their responsibilities. Environmental controls before, during, and after painting. It's vital that paint is applied under the right environmental conditions of humidity, temperature, within dew point parameters, etc. If it's not, then paint will probably fail. Surface preparation, I could go on all day about surface preparation. Basically, the surface preparation is the foundation of the paint system. If you don't get that right, then the paint system is going to fail. Control of application, wet film thickness, and also then the assessment of the dry film thickness. If you don't put the right thickness of paint on, again, too little, the paint's going to fail, or it won't give you the adequate fire protection. Even if you put too much paint on, more isn't necessarily better, because too thick a paint system could actually start to crack and fall off because of internal stresses. So getting the film thickness right is very, very difficult to do, and paint sprayers are extremely skilled trade to do a good job, but the quality control and monitoring of that is very important. Also the integrity of the film in terms of pinholes, holidays, adhesion testing. All these different factors, different stages of the painting process are crucial and have to be undertaken by trained personnel. And training is the absolute mantra. Why the coatings pale? It could be poor design. You know, if you've got a structure with water traps built in there, poor materials, if you've got different metals forming a bimetallic corrosion reaction, poor coating selection, you know, not selecting the right materials for the actual situation. Surface preparation, say that again, can't stress that too much, that the vast majority of coatings failures are down to inadequate surface preparation. Specifications and data sheets not followed. People just start, going back to it's only coated painted, it's covered, it'll do. So incorrect film build, painting in bad weather, missing. If you've got 2-pack paints, it's vitally important that you put the additive into the base components and then mix it properly. People using the wrong thinners, sticking gum wash in there because it's cheap, but it's also colourful contaminants. Misrecoating windows, so all sorts of things can go wrong if the coating operation isn't supervised. And also, hands up, paint manufacturers, sometimes we get it wrong and the paint isn't right for the job. So many different reasons why the paint system could fail, and different extents of failure. So you could have a catastrophic failure. So effectively, example there. Catastrophic failure at the Morandi Bridge in Italy, you may remember a few years ago, collapsed because of an intense corrosion situation due to failure of a coating system. You could have a deflect, just an aesthetic defect. It's not necessarily a failure point, but it could just look bad, and people do like their structure, whatever it is, to look nice. Age degradation, that could be from age or exposure to weather conditions. Coating systems do tend to break down due to ultraviolet radiation, typically chalking, loss of gloss, cracking, that kind of thing. But failure is in the eye of the beholder, and it might not necessarily be a safety critical failure, but if the structure, whether it be a building or a ship or a bridge, whatever it is, if it starts to look shabby and spots of rust, then the owner of that structure isn't going to be very happy. So there has to be analysis of the failure, determine whether it's a premature failure or a guaranteed natural failure, which is due to the natural weathering of the situation. So if someone perceives a failure, is it urgent? Is the job shut down? Is it widespread? Is it very quick? You know, if you got a 20-year spec and there's intense rusting after 2 years, then obviously there's something badly wrong and you need to get in there and investigate. So the inspector then has to go in there and check the specification, were the right products applied, were the right conditions, what correspondence was there, was the specification properly circulated, was it inspected, were the quality control records, and from that detective work, the inspector will hopefully arrive at a decision on what was the quality, the cause of the failure. So to prevent coating failure, use the correct coatings. Obviously, coatings are tested and specified according to the corrosivity and the durability. Surface preparation, keep going back to that one, must be up to standard. Proper application by trained, knowledgeable and skilled applicators, that is vital, because there is a huge spectrum of application skills out there. The vast majority are reputable contractors who will have trained applicators and will do a good job, but there is unfortunately a tendency for white van man to be out there who'll undercut everybody, come along and won't even know what a spray pump is, let alone how to use one. They'll do a bad job, and that will negate any specification. Proper quality control inspection by trained inspectors, then technical service support from the paint manufacturer, and job site visits to overall supervise the job and make sure it's done properly. But read and follow the specifications and data sheets. The tech support team that I manage have an acronym of RTFDS, which is read data sheet. Often people don't do that, and the paint will not be applied properly as a result. So it's down to people to take on responsibility and get themselves trained to know how to do the job. So if there's a problem, is the job shut down, etc. So in this situation, one of the most common defects you see there is the edge deterioration. You can see on the toe of that flange, rust staining and rust spreading from there. Flange edges are a very often underestimated area of the paint job, because paint does not stick well to sharp edges. And so quite often the paint spec will specify that a supplementary stripe coat should be applied onto edges, because quite often even if the thickness is okay on the main areas of that particular section, on the actual sharp edges corners, the paint will draw back from the edges because of surface tension, and you get a low spot on the edge, and very, very often paint will start to deteriorate from that sharp edge. So the best treatment there is, as I say, to stripe coat, or even on the very intensive jobs, you can actually put a radius on those sharp edges, but that's not generally used for structural steel because it's too time consuming and too expensive. But also it's a salt accumulation on horizontal surfaces, and that could also accumulate and accelerate the corrosion mechanism. Fire protection, I mentioned before, is very susceptible to water damage. So these are some examples here of the breakdown you can expect if water gets into an intumescent coating. In my friend Dick Froster's on this call, he said he might be, apologies Dick, because these are photographs of you, so he can sue me for copyright breach afterwards. But typically intumescent, you can see that the beam on the right hand picture where the coating was applied under poor weather conditions, and the coating broke down comprehensively as a result. So any successful coating project depends on quality at every stage. So quality materials, quality contractors, quality specification, and most importantly, quality control. And if you get those four aspects of quality lined up and coordinated by properly trained people, then you will have a successful coating project, which is what we're all after. That's pretty much finishes the very, very rapid helicopter view of protective coatings. I can't stress enough the need for training. If people are interested, the BCSA have recently introduced a training course for responsible coating professionals. Now, this is for people who work with paint as part of their job, whether it's specifying, applying, inspecting, not necessarily inspecting, but using paint, and don't know anything about it and need to. It's not to compete with the existing inspector courses which are out there from people like ANPP, who used to be NACE, or ICO, Frozio. Those courses are defined for people who will be inspecting as a profession. That's what they do as their main job. But people who work with paint and need to know more about it, this BCSA course is basically aiming to improve project quality and reduce failures. Because if people know and understand paint and how to specify, how to inspect, and basically understand the subject, then they can help to reduce coating failures, because coating failures are disproportionately expensive to the actual cost of the paint and doing the job right in the first place. If you do get a coating failure and have to do preventative maintenance, then the cost of that can be very, very, very expensive, and especially the lawyers get involved. Apologies to any lawyers out there, but they're usually the only ones in those situations. But with the right knowledge, then these situations can be avoided. So I commend that you have a look at this course for either yourself or your colleagues who might be interested. The contact details are there at the BTSA. So with that, I'll shut up talking. So I thank you for your time and attention, and I welcome any questions. So,
Thank you very much, Malcolm. You packed a lot of information into that, and there are a lot of questions, which I think reflects how interested people are in this topic. So I'm going to run through the questions. First of all, let's think about the corrosion-resistant coatings. Does ISO 12944 replace Syria 174? Shouldn't we be using Syria 174E and I specs?
It all depends. I mean, I think the Syria specs will largely reflect the aims and ambitions of 12944, and certainly the CDM regulations and other specifications are based around 12944. So I think the two complement each other rather well, and you can probably see some correlation between the two specifications. So what one is not intended to replace the other, and 12944 really is intended to complement Syria specs.
Okay, thank you. Then we're asked, how do you select the classification requirement for external steel in locations around the UK? And how often should you carry out an inspection if a very high durability paint is used?
That's an excellent question. I think I mentioned the scientific way of doing it, and there is another engineering standard which actually defines those corrosivity measures, which, as I say, entails putting specimens into that environment and measuring the rate of metal loss, which of course people can't afford to wait to do that. So the 12944 standard does give verbal descriptions, and it's largely a case of agreement. And it's often quite contentious because obviously the higher the corrosivity, the more paint goes on, so the more expensive the paint spec. But you have to be careful. You know, we as paint manufacturers are naturally more conservative, because we sell more paint. But you know, joking apart, we don't want to see any failures. But obviously, people might be tempted to define it as a lower environment, depending on the environment. But you know, it's a case of pragmatic agreement, really. I think if you can't agree, then you know the paint manufacturer would certainly enter discussions, and then maybe a site visit to speak to people, and maybe get an independent inspector to come along for their opinion as well, and generally come to an agreement about what the site might be. Because the classic example of a job in Liverpool where you know you look to the job one way and it's Liverpool city centre, and oh yes, that's a C3, but you look the other way and you can see the Irish Sea. So that's C4 bordering C5, you know. So yeah, you have to come to some compromise in some certain situations. In terms of inspection periods, these will be again to be agreed. Paint manufacturers, I know we certainly have our own recommendations for inspection periods depending on the environment, but that will be, you know, if you speak to your paint supplier, they will be able to offer recommendations on that subject.
Thank you. Then the final question on the corrosive resistant paints, corrosion resistant coatings, is can you talk through the implication from a factory application perspective of applying zinc rich paint, what that means practically, as compared to galvanizing? And the person is asking for a cavity situation where it's inaccessible but potential for moisture.
Yeah, good question again, because inaccessible situations obviously can't be inspected, so thereby you would be expected to provide an absolutely bulletproof paint specification for somewhere that's going to effectively last the life of the building. Galvanizing is a very effective method of corrosion protection, and you know, obviously, as a paint manufacturer, you know, galvanizers are in some cases competitors, but I do respect galvanizing as a highly effective method of corrosion protection. But zinc-rich primers, which are these primers which have a very high zinc metal content, will also give you an equivalent corrosion protection within that particular situation. So it's horses for courses. Some people will decide, yeah, we'll use galvanized steel. Others will decide on an in-shop zinc-rich primer. They're both effective methods of that protection in that situation.
Okay, thank you. Now we've got another 20 questions. We won't have time to answer them all, but let's move to intumescent coatings. So on a recent project, the architect stated insurers would not accept intumescent paint. Can you comment on this? Is this an issue with architects?
I suppose that you'd have to ask the architect that question. I mean, obviously, there are, again, many different ways of fire protection. You know, the intumescent coatings are one. You can board a situation. You can have cementitious, there are, many different ways to skin a cat, so to speak. So I can't comment on whether that particular architect had a bad experience with intumescent coatings or not. They're all certified and in my opinion, worthy methods of protecting against the fire situation. So I can't comment on that particular architect's viewpoint.
Yeah. Okay. Let's talk about clearance. For intumescent protection, is there a minimum clearance required around the steel section to allow the coating to expand? In fact, there are a few questions more or less the same.
Yeah. We get asked many questions about these, if you like, the nitty-gritty of steel design and etc. And typically, you have to allow an expansion gap for the intumescent to do its job and create that effective carbon blanket. Otherwise, if it's restricted, then it can't do its job. So speak to your paint manufacturer on that. Typically 50 millimeters is given as a figure. Sometimes the reductions will be allowable. If the restriction is created by, say, for example, a boarding, if that boarding is itself fire approved, then you'll have the protection from the, if you like, the reduced intumescent plus the boarding. So in that case, a reduced gap would be allowed in certain situations. That scenarios will be simulated and fire tested. So in that case as well, allowance will be given to reduce that, if you like, the standard gap. But everything nowadays has to be tested and certified. We can't give opinions post Grenfell for obvious reasons, but even educated opinions and 99.9%, yes, it'll be all right, isn't good enough. You have to have that particular certificate in place now to have a validated fire protection system.
Thank you. How much variation do you get in the performance of intumescent coating? Say if you tested 10 identical specimens, what percentage variation in steel temperature might you expect?
That's a good one. There will certainly be margins of error within the test standards. I couldn't, off the top of my head, give you what the margins of error are, but I think certainly a given product, if it was tested 10 times in the same furnace, would have to be within a certain percentage limit. I couldn't tell you honestly off the top of my head what that plus or minus factor will be, but certainly manufacturers will obviously do the fire testing initially, and then they'll weather samples and bring samples in after a period of weathering, and the weathered sample has to be within a certain percentage of the original unweathered control, if you like. So the figures do exist, but I apologise, I couldn't tell you. I would like to guess. So.
That's fine. Now, in fact, this is a question that I was going to ask, but someone else has got in first. For reasons of sustainability, we're encouraged to reuse structural steel sections. And when reusing fire-painted steel, can the coating be reused in whole or in part, or does the steel need to be blast cleaned and repainted?
I think we would probably recommend, and again, certainly post Grenfell, that the whole system has in its entirety a brand new certified system on there. You could have a system that's been out there, intumescent coating has been out there, 20 odd years now. So if something came in and, oh yes, we'll reuse this steel, it's 20 years old, and it had an approved intumescent coating from 1998. Let's reuse it and all that intumescent to be all right, because it's still intact, it still looks good. I think if it's a new installation now, it would have to have a new freshly applied intumescent system. Even though yes, it might intumesce in the fire, it might give you fire protection. I'm afraid might is no longer good enough nowadays. It's got to be you've got to have all the I's dotted and T's crossed. Otherwise, you're going to be held to account if that system doesn't perform subsequently. And quite often you just don't know what the fire protection was. So it's difficult to, you can't identify what it was, and you can't verify.
Yeah, thank you. I'm just going to ask you two more, if that's okay. So, yes, this one. For site-applied intumescent coatings, can these be applied to steel exposed to weather or rain? And if so, is there a time limit that the coated steel can remain exposed until it's covered by structure and protected from the elements?
Excellent question. That doesn't apply just to fire protection, it applies to corrosion protection as well. You have to take into account the transport and storage and erection phases of the project. And even though you might have a steel that's going to a C1 environment, if that steel is going to be sat on the site or even a dock side for 6 months, 12 months, then you have to apply a coating system that will be robust enough to withstand that transition phase. And the same goes for passive fire protection. Major 4 then, I called it passive fire protection. It's not, it's reactive fire systems, and that's a classic mistake, that intumescent coatings aren't passive, they are reactive. So eliminate that last 4 but reactive fire protection systems, you have to supply protection that will be adequate for that construction phase. So even though it's going to be internal steel during the building working life, and it's going to be exposed for 6 months, 12 months, it could be in a C5 environment, then you have to apply sufficient protective sealer coat to protect that fire protection from the elements during that phase. Otherwise, it will break down during the interim period and not perform. And it's intended function. So the construction period is a vital consideration. So very good question.
Yeah. And then finally, of the questions we'll deal with verbally, can intumescent coatings be subjected to accelerated aging tests to determine a potential lifespan or warranty period for a given set of environmental conditions? And is this covered by a relevant standard?
Yeah, that would be covered. I mean, the main standard for durability of fire protection systems is the European EN 13381, which has a variety of exposure periods for internal steel, external steel, semi-exposed steel, with and without a weathering period. So that standard does actually take into account whether the steel will be exposed for, I think it is up to 6 months. So that EN 381 will give you, as part of the declaration performance of that, according to the European standard, to effectively dictate whether that coating system will or will not withstand external weathering.
Thank you. Big thank you to Malcolm. We will gather together the other questions. They're still coming in, actually, and email them to Malcolm, and he may be kind enough to answer you directly. Obviously, a huge amount of interest in this topic. And I just wanted to add that here at SCI, we're finding clients are coming to us asking us to carry out thermal analysis of hot rolled or light gauge steel, whether it's protected with intumescent coating or unprotected. Clients are wanting to find out the response of different types of construction details to fire. So if that's of interest to you, please don't hesitate to get in touch. So many thanks, Malcolm, and I'll say goodbye now. Bye.